Hi, welcome to this week's installment of the Nobel Review. My name is Matthew He, your faithful host, and today we'll be examining Dr. Arthur McDonald. Dr. Arthur McDonald is a Nobel Prize recipient for the Nobel Prize in Physics for 2015. Now, his prize motivation is for the discovery of neutrino oscillations, which shows that neutrinos have mass. Let's take a closer look at Dr. Arthur McDonald. Arthur Bruce McDonald was born on August 29, 1943 in Sydney, Nova Scotia. He earned his bachelor's and master's of science from Dalhousie University and went on to earn his PhD in physics at the California Institute of Technology. From there, Dr. McDonald went on to work as a research officer at the Chalk River Nuclear Laboratories near Ottawa. He then became a professor of physics at Princeton University for 7 years before leaving America to join Ontario's very own Queen's University. In May 1999, he stepped up to direct a 7-year experiment in the Sudbury Neutrino Observatory, which would eventually earn him his Nobel Prize for Physics in 2015. He is currently the University Research Chair at Queen's University and a board member at the Perimeter Institute for Theoretical Physics. Dr. McDonald's educational background and his country of residences have both played a significant role in his work as a physicist. In an interview with Dr. McDonald, it was learned that his high school math teacher, Bob Chafe, had greatly inspired him to pursue a career in the mathematics and the sciences. Later, in Dalhousie University, he was encouraged by his professor, Ernie Guptill, to become specifically involved in physics. Now, Dr. McDonald primarily lived in Canada, more specifically, Ontario. The multicultural environment of Ontario led to many international collaboration opportunities during Dr. McDonald's career. He's worked with the USA, the UK, Canada, Portugal, and eventually Japan in numerous major projects, one being the collaborative effort of the Sudbury Neutrino Observatory. The encouraging teachers and mentors he's met on his path, and the multiculturalism of Canada, has both played a crucial role in his work as a physicist. Now, speaking of his work, Dr. Arthur McDonald has contributed significantly to over 153 recognized publications. His most important publications include Measurement of the Cosmic Ray and Neutrino-Induced Muon Flux at the Sudbury Neutrino Observatory, and Evidence for Neutrino Oscillations 1, Solar and Reactor Neutrinos, which were both key publications that led him to winning the Nobel Prize in Physics for 2015. Dr. Arthur McDonald has dedicated his entire physics career to investigating whether or not neutrinos oscillate. Now, neutrino oscillation simply means that a neutrino created with a certain flavor can later be measured to have a completely different flavor. In other words, it changes its own identity. Now, to understand his research, we must divide it up into 3 parts. 1. What are neutrinos? 2. How did Dr. McDonald perform this experiment? And 3. What are the underlying physics principles behind discovering neutrino oscillation? Sounds like a lot, so let's begin. Now, to answer the question of what are neutrinos, we must first understand elementary particles and atoms. Elementary particles are particles whose substructure is unknown, which implies we can't tell whether it is composed of other particles or not. Elementary particles are the basic constituents of ordinary matter. Atoms, despite the Greek root atomos meaning indivisible, are not elementary particles, meaning they can be disassembled. An atom is really just a diffuse cloud of electrons surrounding a tiny, dense nucleus composed of protons and neutrons, which can be broken into up and down quarks. Out of the 4 fundamental forces of the universe, neutrinos are only significantly influenced by one. They are not affected by the electromagnetic or strong nuclear forces that bind nuclei and atoms together, and its small mass means that gravity barely affects it. Only the aptly named weak nuclear force influences it. Neutrinos are everywhere around us, nearly a trillion pass from the sun to your eyes every second. However, their limited interactions means that they are rarely observed. They come in 3 seemingly stable types called flavors: electron, muon, and tau neutrinos, corresponding to the 3 charged particles they pair with. Because the 3 flavors of neutrinos are almost identical, there is the theoretical possibility that they could change into each other, which is an unusual aspect of these particles, one that can reveal new physics. This transformation requires 3 things: that neutrino masses are non-zero, are different for different flavors, and that neutrinos of definite flavor are quantum combinations of neutrinos of definite mass. So, how did Dr. McDonald perform his experiment? This experiment was performed in the Sudbury Neutrino Observatory, located 2,100 meters underground in the Creighton Mine of Sudbury, Ontario. The detector is designed to detect solar neutrinos through their interactions with a large tank of heavy water. Prior to the existence of the SNO, all experiments regarding neutrinos observed a third to half fewer neutrinos than that predicted by the standard solar model. As several experiments all indicated this, particle physicists around the world gave it a name: the solar neutrino problem. Decades of academic research resulted in the proposal of numerous hypotheses explaining this problem, one which hypothesized the existence of neutrino oscillations. The SNO detector target consists of 1,000 tons of heavy water contained in a 6-meter radius acrylic vessel. Heavy water is a naturally but rare occurring isotope of water, where the 2 hydrogen atoms are replaced by 2 deuterium atoms, which each has one more neutron in its nucleus than hydrogen. The detector cavity outside of the target is filled with normal water to provide both buoyancy and radiation shielding. The heavy water inside the target is viewed through 9,600 photomultiplier tubes, which are simply extremely sensitive detectors of a broad range of light. These photomultiplier tubes monitor the heavy water for any charge current interactions, neutral current interactions, or electron elastic scattering caused by neutrinos. Now, these are the physics principles behind Dr. McDonald's experiment. But let's take a look at what they actually mean. In a charged current interaction, a neutrino converts the neutron of a deuterium atom to a proton. The neutrino is absorbed in the reaction and an electron is produced, which carries an energy measurable by the photomultiplier tubes, indicating its occurrence. In a neutral current interaction, a neutrino dissociates a deuterium atom, breaking it into a proton and a neutron, while the neutrino continues on with slightly less energy. The neutron from the broken deuterium would be quickly captured by another deuterium nucleus, which would produce a measurable amount of energy, thus indicating its occurrence. In electron elastic scattering, a neutrino collides with an atomic electron and gives some energy to the electron, which is detectable by the photomultiplier tubes. The 7-year experiment was concluded by many more years of data analysis. In simple summation, the results found that the total number of neutrinos observed, when taking into consideration all 3 flavors of neutrinos, actually corresponded to that predicted by the standard solar model. What this means is that those neutrinos must have oscillated through the sun before traveling to the Earth. In turn, this means 3 very important things. 1. Neutrinos of mass. 2. Neutrinos of different flavors have different masses. And 3. A neutrino of definite flavor would be a quantum combination of neutrinos of definite masses. Now, all this was not included in the standard model of particle physics. Therefore, this changes everything. Now, as I previously mentioned, Dr. Arthur McDonald shares his Nobel Prize with a fellow researcher. This researcher would be Dr. Takaaki Kajito of Japan. I have here with us today Mr. Ada Artin, a student studying Dr. Kajita's work. And he's going to tell you a bit more about Dr. Kajita and his influences and his impacts in Japan. Go ahead, Ata.
Hey Matt, I heard that you want to learn more about Takaaki Kajita. Well, Takaaki Kajita was born in 1959 in Higashimatsuyama in Japan, and is a Japanese physicist who received a bachelor's degree from Saitama University in 1981 and a doctorate from the University of Tokyo in 1986. That year, he became a research associate at the International Center for Elementary Particle Physics at the University of Tokyo, where he worked on the Kamiokande neutrino experiment, a tank containing 3,000 tons of water located deep underground. In 1988, he inferred neutrino oscillations from the observation of atmospheric neutrinos in the Kamiokande experiment. In 1992, Kajita and his team published results confirming the deficit of atmospheric muon neutrinos. They suggested that neutrino oscillations in which the missing muon neutrinos change into a third neutrino flavor, tau, which could not have been observed by the Kamiokande experiment that was currently carried out. Through conducting and leading The second project, the Super Kamiokande experiment, containing 50,000 tons of water in it, Kajita was able to confirm his discovery of the oscillations of neutrinos from one flavor to another, which proved that dozens of subatomic particles have mass. For this very reason, from a Japanese point of view, Takaki Kajita is recognized more as the figurehead of the discovery. But I believe that both researches that have been carried out are very promising to evolve our current understanding of the standard model of the innermost workings of matter. Hope this helps, Matt. Thanks.
Thank you very much, Ada. It's absolutely fascinating to learn about another perspective. Now, to continue on the theme of global impacts, the discovery of neutrino oscillations has had significant impacts on both the scientific community and society as a whole. To the scientific community, neutrino oscillation solves the solar neutrino problem and provided an update to the standard model of particle physics. This furthers our understanding of the universe. For the general public, a recent breakthrough in communications occurred when a coherent neutrino message was sent by a particle accelerator through 780 feet of rock. This shows strong potential in future use of neutrinos to send messages across immense distances through previously impenetrable materials, such as the Earth's core. Scientists have already begun constructing the conditions of the Sun's core through observations made from incoming neutrinos. Neutrino oscillation also plays a role in the astrophysics community for both researchers and enthusiasts. When a supernova occurs, neutrinos are the only particles capable of escaping the core front, and the sudden release of neutrinos can be picked up by neutrino telescopes on Earth and allow the astrophysics community to prepare for observations and measurements of the collapsing star. The field of neutrino applications may very well grow to exceed the costs associated with its discovery. And since the confirmation of neutrino oscillations only occurred very recently, we must look towards the future of the application of this phenomenon, with both curiosity and an open mind. Well, that concludes the life and achievements of Dr. Arthur McDonald up to this date. Thank you for tuning in to this week's installment of the Nobel Review. My name is Matthew He, and I'll see you next week. Same time, same place. Bye-bye.